and the organic chemistry department is proud to
Present.
present.
You mean presents?
No, present. Present.
Present.
I think our script writers need spell check. Either way, today we are going to learn about molecular orbital theory. So let's get started.
So, molecular orbital theory is one of those things that look a lot worse than they are, so let's get right into it. So, molecular orbital theory is one of those things that seems kind of bad, but once you actually get into it, it's not too terrible. So, first thing we're going to do is notice that this is a diene. It's actually 1,3-butadiene. And every one of these carbons is sp2 hybridized, so we're going to have this p orbital that I have drawn in blue. And each of those p orbitals contributes one electron, as I've drawn in orange, and each of those electrons will form our pi bonds, which is our double bond. And I've already drawn it in black or gray, how we would usually do it, but I also wanted to show you another notation on how to draw that. So, when we look at the 4 atomic orbitals, which is what I've already drawn, we can label 4. And in this class, since we're only talking about pi orbitals anyway, the number of atomic orbitals and molecular orbitals will be equal. And then when we're looking at the pi electrons, all we have to do is go through and count how many electrons we have. 1, 2, 3, 4. And in this case, all of the carbons are each giving 1 electron. So now, when we actually go to drawing our molecular orbital diagram, let's zoom in, we have to go through and figure out what these orbitals on the side are going to look like. So on the bottommost energy level, all of them are going to be filled in on the same side, like such. And the reason for this is if they are all filled out on the same side, they're all in the same direction, that means there is the lowest energy, there's no nodes in between. Every time we go up an energy level, we add a node. So in level 2, we will have 1 node, and at the node is when you flip sides. So bam, node equals flip. And in the 3rd energy level, we are going to have 2 nodes, like so. So we have up, down, down, up. And in the last one, we have a node between each orbital. So we have up, down, up, down. Now we're going to go through and just place our electrons. Since we have 4 electrons, we start at the bottom and we do 1, 2, 3, 4. And remember that we are going to fill up 1 energy level before we can move on to the next. And one thing I want to point out to you guys is this is the ground state. This is our regular old home state that we like to be in. Now I have something on the side labeled bonding versus antibonding orbitals. And essentially what this means is the bonding orbitals are the ones that have electrons in them that are ready to make bonds. The antibonding is the higher energy levels that essentially correlate with the bonding orbitals. And the reason I say correlate is because I want you to think of them as being a pair. And by that I mean, like, let's say pi 4 and pi 1 are a pair, pi 2 and pi 3 are a pair. If you think about it this way, it'll help you in the future because you have to remember that there's always going to be an equal number of bonding and anti-bonding orbitals. They will always equal each other. Another way to write antibonding is this little star as I've drawn here. The last thing we have to fill in is the HOMO and LUMO, and I've written out that word on the side, but let's just define it. So LUMO is the lowest unoccupied molecular orbital, and the HOMO is the highest occupied molecular orbital. And so as we can see, this is the highest energy level with electrons in it, so it will be the HOMO, and pi 3 is the lowest orbital energy level that has 0 electrons in it, so that's why it is the LUMO. When we go into the excited state, before I say anything, you have to note that these names don't change. So this will still be bonding, bonding, antibonding, antibonding, and this will be HOMO and this will be LUMO. The names don't change. And the reason for this is because you can think of each of these energy levels as a container. So if you have 4 containers and each of them hold a specific thing. So let's say the bonding electrons hold red balls and the antibonding hold green balls, right? If you accidentally put a red ball into the green bin, then it doesn't become a red bin. It just becomes a green bin with a red ball in it. So pretty much the same concept can be applied when we talk about electrons. When we excite this molecule, these 2 electrons will stay put, one of these will stay put, but the other one will jump up to the next highest energy level. And this jump is always going to be most favorable and most likely going from the HOMO to the LUMO. So when we get excited, when we go from ground to excited, 1 electron jumps from HOMO to LUMO. And again, the reason the naming here doesn't change is just because the electron went into an antibonding bin does not mean that this bin becomes bonding. It just means that we temporarily have an electron in it. So to recap, 1,3-butadiene has 4 atomic orbitals, 4 molecular orbitals, and 4 pi electrons. We have 2 bonding orbitals and 2 antibonding orbitals. And in the ground state, we have 4 pi electrons in bonding orbitals and 0 pi electrons in our antibonding orbitals. And we know that the HOMO is pi 2 and the LUMO is pi 3. And in the ground state, there are 0 electrons in the LUMO and there are 2 electrons in the HOMO. In the excited state, however, there are now 3 electrons in our bonding orbitals and 1 in our antibonding orbital. So HOMO is still pi 2, LUMO is still pi 3. However, now there is 1 pi electron in the HOMO and 1 pi electron in the LUMO. And that's it. We finished our first one. So now we are going to cover the allylic cation, or the allyl cation. And the important thing to note here before we even get started is that this cation means that we have an empty p orbital. So one thing that you may not have learned in Orgo 1 is that cations, anions, and radicals are all going to count as being sp2 hybridized. So in this case, this is conjugated all across, and we do have 3 pi atomic orbitals. And that translates to 3 molecular orbitals. But if we count the number of electrons, we know that a cation means that we have a positive charge, which means this p orbital is empty. And then for the double bond, we have 1 electron per orbital, so that would be 2. And now when we go to put our electrons into our orbitals, we first have to change this little orbital diagram. So before we had 4 orbitals to fill in, now we only have 3. And we know that on the bottommost energy level, all of these orbitals will be shaded in on the same side. So it has the lowest energy. We're going to add a node in the second energy level. But the important thing to note here is that the node will actually go right here in the orbital. So it's almost like this orbital disappears. So we have up and down. And then in the third energy level, we have 2 nodes. So we have a flip between each orbital. The reason this middle layer is so important, and we need to understand that, is because the middle energy level, orbital will have no electron density in it ever, because that's where the node is. So with that, and also the fact that we have 3 energy levels now, and I told you guys the number of bonding and antibonding has to be equal, we have to introduce a new term. So non-bonding, for the purposes of this class, you can just think of non-bonding as a space filler. So if we ever have an odd number of energy levels, we know that the number of bonding and antibonding has to be equal. So whatever that extra remaining one in the middle, wherever that is, it will be a non-bonding, because we know bonding has to equal antibonding. Another way we can think about it is that this one in the middle that got messed up because of the node, we can call that non-bonding because there's no electrons. We can think about it that way. Whatever helps you the most. So when we're filling in our electrons, again, we're going to start at the bottommost energy level and work up, but now we only have 2 electrons. So only in the bonding orbitals. In the excited state, though, one of these will jump up to pi 2. So we get bam, bam. At this point, we can name our HOMO and LUMO, and we have to look at the ground state for that. So our lowest energy level with no electrons is pi 2. And our highest energy level with electrons is pi 1. So we can safely say that pi 2 is our LUMO and pi 1 is our HOMO. And if you guys remember, we are not going to change the naming in the excited state. So we know that pi 2 will still be LUMO and pi 1 will still be our HOMO. So to summarize, for the cation, we have 3 atomic orbitals, 3 molecular orbitals, and 2 pi electrons. In the ground state, we know that we have 1 bonding orbital with 2 bonding electrons, 1 non-bonding orbital, but 0 non-bonding electrons, and 1 antibonding orbital with 0 antibonding electrons. In the excited state, none of the naming changes, but now we have 1 electron in the bonding orbital, we have 1 electron in our non-bonding orbital, and 0 in our antibonding orbital. Excuse me. So moving on to the allylic radical, it's essentially very, very, very similar. So I've gone ahead and already filled out a few things, but the difference then comes in to the number of electrons we have. Having a radical means that we have 1 electron by itself in this p orbital. So altogether we have 1, 2, 3 pi electrons. Bam. And I just noticed that I accidentally already wrote in the HOMO and LUMO, so I'm sorry for giving that to you before I talked about it, but that's okay, we're still going to talk about it. So now that we have 3 pi electrons, we're going to go ahead and fill in 1, 2, 3. Uh-oh, this is super unstable because we have a half-filled energy level. And if you guys remember from Orgo 1, radicals are super reactive, they're super weird, and the reason they are this way is because of this half-filled orbital. But that's just a little fun fact. So as we can see, pi 2 is the highest energy level or highest molecular orbital that is occupied. So we were correct in naming this the HOMO. And pi 3 is the lowest molecular orbital that has 0 electrons. So we were right in naming this the LUMO. In the excited state, we are going to jump up from the pi 2 to the pi 3, aka from the HOMO to the LUMO. And now we have a little bit of a weird situation because this middle non-bonding is empty. That's kind of strange. So, kind of to recap and summarize, we have one bonding orbital, one non-bonding, and one antibonding, Pi 2 is the HOMO, pi 3 is the LUMO, and that is again the same here. The difference comes into the number of electrons in each orbital. So we have 2 bonding electrons in the ground state, 1 non-bonding in the ground state, and 0 antibonding electrons in the ground state. In the excited state, we still have 2 bonding electrons, but we have 0 non-bonding electrons and 1 antibonding electron. When we go on to the allylic anion, this is when it's a little bit fun because the anion has 1 more extra electron here. So we still have the same number of atomic and molecular orbitals, which is 3, but now we have 4 electrons. So if we go through and bam, 1, 2, 1, 2, we can see that we have this now filled non-bonding orbital. In the excited state, one of these will jump up into the LUMO, so we get this. So for the allylic anion, you guys should know that you have 3 atomic orbitals, 3 molecular orbitals, and 4 pi electrons. You're going to have 1 bonding orbital, 1 non-bonding orbital, and 1 antibonding orbital for both the ground and excited states. The HOMO is pi 2, and the LUMO is pi 3 in both ground and excited states. The difference is the number of electrons again. So we have 2 bonding electrons in the ground state and 2 non-bonding electrons in the ground state. And of course, 0 antibonding electrons. In the excited state, we have 2 bonding electrons, 1 non-bonding, and 1 antibonding electron. So as you guys can kind of see, molecular orbital theory looks like a lot, but it's not actually too much that you guys have to know for this class. All you really have to know is what an orbital is. So just know that a pi bond means that you have p orbitals, and also if you have a cation, anion, or radical, that also means you have a p orbital. And then remember that the number of bonding and antibonding orbitals has to be equal. So if you have an even number of orbitals, you will only have bonding and their corresponding antibonding orbitals. If you have something like the cation or the anion or the radical that has 3 orbitals, that's an odd number. So you have to have 1 non-bonding electron to balance the bonding and antibonding out. And that one will go in the middle. And another way that we name orbitals is the HOMO and the LUMO. HOMO meaning highest occupied molecular orbital, LUMO meaning the lowest unoccupied molecular orbital. And when we go into the excited state, one of our electrons will jump up from the HOMO into the LUMO. Between the ground and excited state, the names do not change. So the orbitals are like our little containers, our little buckets, and the names of these buckets do not change. The only thing that changes is what is inside of them, aka the electrons. And that's all you really need to know. I hope you guys have a great day. Bye-bye.